Lab 4, Spring Mass System, Physics 2211, Section N. The goals. One of the goals of this lab was to expound upon the motion oscillating on a spring to simulate the physics of extreme sports with ropes. We also created a model in order to compare model predictions with analyzed data from Tracker. Secondly, we applied the fundamental principles such as the momentum principle and the energy principle, as well as concepts such as Hooke's law. And in the end, it was showcased that the spring mass did indeed satisfy the energy principle. In this lab, once again, the fundamental principle and Newton's second law were used. Vf equals Vi plus F net over m times delta t was used to calculate velocity, and the position was again updated as in previous labs with Rf is equal to initial position plus V average delta t. Several other physics concepts were explored in this lab. It was shown that the net force, was equal to the force of the spring plus the force of gravity. Analysis of the energy based on system consisted of the Earth, the spring, and the mass. Since there were no interactions in surroundings, we can conclude that the delta E, the change in E, and energy was equal to the change in kinetic energy plus the change in use of spring and use of gravitational, and this whole summation adding up to 0. E kinetic was equal to 1/2 mv squared, while U of spring is equal to 1/2 k times s squared. U gravitational, on the other hand, was equal to mgh. These concepts were later coded and used in VIO to create the graphical representation of the oscillation in spring motion. Here, moving on to Tracker, we can see that I created the axes with the positive x pointing toward the right and the negative x pointing towards the left. The negative y was pointing downwards and the positive y upwards. Additionally, we used a calibration stick to get the known distance of 0.7 meters in order to track the data. We started tracking immediately when the force was pushed on to the pendulum. And here is the object in motion. As you can see, we tracked the position as it moved through, and we represented each movement with a dot, and this was later recorded and put into data on a graph. This graph right here represents time versus x position. Using the data from Tracker, we imported it and converted it into a CSV file, which we later used in VIDLE here. This is the program which we created in order to represent the graphical representation of the object in motion. Here we set the ball mass and initialize the position and initial velocity. Here's where we read the data from the CSV file. We set a small time step. We set constants such as gravitational force, K sub s, L naught, L hat, and S. S in particular describes the stretch and compression of the spring. So when S is actually greater than 0, there's a stretch, and when S is less than 0, there's a compression of the spring. We computed the system energies with the kinetic energy of the spring mass system, gravitational potential energy, and spring potential energy of the spring mass system. We set the time loop equivalent and correlative to the time video with 9.307 seconds. We defined the initial energies. Next, we calculated the gravitational force, the net force, Newton's second law to update the position as we normally do, and then we updated the spring. Once again, we calculated the energy, and then we plotted it using this formula right here. And here is our final product. As you can see, the blue line represents delta K, the red line represents delta U sub S, and the green line represents delta U sub G. And this yellow line right here is a summation equaling 0, showing that everything was included as a part of the system, and that there were no surroundings. And here's the motion in the graph, as you can see. Here's the lines I was referring to earlier. And now let's move on back to the PowerPoint. Some of the calculations in this lab were calculated with the period denoted by t representing the time required for one complete oscillation of the spring. T was equal to 2 pi times the square root of m over k, and also we found the relaxed length where at static equilibrium the gravitational force and the spring force were equal. mg was equal to k sub s times s, and mg was equal to k sub s times L minus L naught, and here we isolated L naught by itself in order to use it and calculate for it its value. The discussion questions. The first question asks, for your model system, is the energy principle satisfied? This question is answered with the graph shown here. As you can see, the energy principle is satisfied because the summation of delta K, delta U sub S, and delta U sub G gives you a line that's totaling 0, depicted by the yellow line. and this shows that it's true. The second discussion question of this lab says, using the data you obtained from Tracker, make two separate estimates of the oscillation periods. First, by estimating the period of oscillation from the X position data, and second, by estimating the period of oscillation from the Y position data. Compare the two estimates and discuss. This graph represents the solution to that question. As you can see, the periods are very similar with the average period of 1.5 seconds. So it is not exactly clear to say, but we can, by looking at exact values from Tracker, we see that the periods are longer for the X than they are for Y. In conclusion, the lab effectively expounded upon the motion oscillating on a spring to simulate the physics of extreme sports with ropes. The model predictions with analyzed data from Tracker were close to each other. Fundamental principles such as the momentum principle, energy principle, and concepts such as Hooke's law were used to satisfy the energy principle. Lastly, the line representing the change in E kinetic plus the change in U spring and change in UG was 0 throughout, satisfying the question posed earlier. Thank you for your time, and I hope you've learned a tad bit from my lab explanation.